gives you xi plus 1. That's the reason. That's the picture. Okay.
Your crossings get Q, right? Or Q inverse.
The crossings are done in such a way that they
No, I mean, if it breaks back, call it Q or Q inverse, depending on how.
Yeah. So, yeah, but if you use T and X, then things go through nicely. Yes. Okay, so here is the more interesting one. I told you there was this relation, nasty relation between X and Y, right? So you can rewrite it in this way. So a certain condition on X and Y should be equal to a T squared. So here is my condition on X and Y, Y2 inverse, X1, Y2, X1 inverse. Okay? So let's look at this and try to pull the string. So it's a bit difficult because we work on a torus. So we have to remember that everything on the right is identified with everything on the left, and everything in front is identified with everything in the back. Right? It's 4 matryoshka. Okay? So what it means is that this connection between these 2 points here, I can reproduce in purple here, right? Just because it's torus. And the connection between the 2 fronts points here, I can represent in the back as well. Okay? And then I can pull my strings. And but I end up with a knot here, right? And it's D1 squared. Okay? So all the relations are pictorial, except of course the ones we impose on top. Okay. So let's go now towards McDonald theory. What is good about this double affine Hecke algebra is that it allows you to tackle very nicely and very elegantly the McDonald polynomials. Okay. So it starts with the polynomial representation, and I already jumped to the conclusion by saying spherical here, meaning that I'm already concentrating on symmetric polynomial representation. I don't have to, in which the t's are expressed in terms of the x's and of this operator, which is just a transposition, elementary transposition, interchange of 2 neighboring x's. Okay? And so if you now act on polynomials with such operators, they will satisfy all the relations of the algebra. Okay? This pi, I told you, was this cyclic rotation of the points, will act nicely also on all the generators. And at the end of the day, you can rewrite the y's in terms of these t's, this pi, okay? And you can compute elementary symmetric functions of these y's. And magically, there appear the QT McDonald operators here. Okay? So the very same ones that we were looking at before, except I had a t here and a 1 there, so theta squared t, it's not a big difference. Okay? So I reproduced it. Therefore, these guys now are actually the exact good operators, such that their common eigenvalues are these McDonald polynomials. And actually, there's also a theory of non-symmetric McDonald polynomials that looks at the y's instead of at their symmetric functions. Okay. But anyway, here is the new theorem that we found, that we can now upgrade these y operators to yin, depending on time, now n, in the following way, right? So we almost conjugate the y's with something dependent on the x's. Then we can prove that this forms a commuting family in the double affine Hecke algebra. And then in the spherical representation, the operators just become like this. So it's just an insertion of z to the n in front. So that should remind you something, because our definition of a Q affine was precisely an insertion with z to the n. And indeed, the corollary here is that our operators satisfying the quantum cluster algebra are limits when theta goes to infinity of these new operators, d alpha n. Okay? So we have a formulation within Daha with new operators of this solution of the quantum Q system, which allowed us to solve our problem. Okay? And this is the big picture. I didn't want you to miss it. So we started somewhere around here. We used quantum cluster algebra in the form of quantum Q system via this constant term formula. We used discrete integrability to get difference equations for those guys. And then we used double affine Hecke algebra, or certain limits thereof, to formulate solutions of this equation. So essentially, I've been treating this part of the diagram. Now, Daha is also useful not just for the theory of McDonald polynomials, but also for torus knots invariants, as you can see, because my matryoshka, they have everything to do with knots, right, in this representation. Okay, and then there's limits you can take. Okay, and in particular, the continuum limit of quantum spin chain is supposed to be conformal field theories, some special conformal field theories, within which you can get more connections between objects in this QT deformation that we came up with trying to reproduce our operators. And the master word here is this AGT connection, which would be the final word about this diagram. But I don't want to say anything more about this. Okay. Thank you.